Dear friends, I myself, Dr. Bharat Parab, discussing the topic use of Euclid's postulates to prove other results. Which use or applications of Euclid's postulates. Okay, by the help of these Euclid's postulates or axioms, we will be proving other results. Okay, that is what it means. So, example one, read this very carefully. If A, B, and C are 3 points on a line, see here. Okay, and B lies between A and C. See the figure below. Okay, A, B, C. So B lies between A and C. Okay, that is what is given. Then prove that AB plus BC, AB plus BC is equal to AC, is equal to AC. Okay, now here TPT, that means to prove that AB, AB plus BC plus BC is equal to AC, is equal to AC. Now solution, there is some comment given here, some argument. You will come across such type of arguments very frequently in geometry, and try to understand this very carefully. Okay, see in the above figure, AC coincides with AB plus BC. See, if you take AB and again add BC to this, you take AB and add BC to this, that means it coincides with AC. Okay, this is same. Okay, so it should be in geometrical language. In the above figure, AC coincides with AB plus BC. Okay, then see here, but by Euclid's fourth axiom, which states that fourth axiom taken as it is with number, things which coincide with one another are equal to one another. Okay, that means if they coincide, they will be equal to one another. So AB plus BC coincides with AC. Okay, that means they will be equal. That is what is given. So we can say that AB plus BC equal to AC. Okay, so we are here using Euclid's postulates and axioms to prove this. Okay, second example, prove that equilateral triangle can be constructed on any given line segment. Okay, this is some segment given AB. So you will see in the solution. Solution, as given in the statement, a line segment of any length is given as AB. Okay. Now, according to Euclid's third postulate, which states that a circle can be drawn with any center and any radius. Okay. This is the third postulate. So, taking help of this, we can draw a circle with A as center and AB as radius. This is a center and AB as radius. We have drawn this circle. Okay, and another circle with B as center and BA as radius. B as center and BA as radius. Okay, this center, this circle. Okay, these two circles meet at C. Okay, now join AC and BC to form triangle ABC. Okay, triangle ABC. Now see here, AB is equal to AC because these are radii of same circle. Similarly, BA is equal to BC. BA is equal to BC, radii of same circle again. Okay, first time it was this circle, second time it was this circle. Okay, hence by Euclid's axiom that things which equal to same thing are equal to one another. That means is AB is equal to AC, and again AB is equal to BC. That means AC is equal to BC. That is what it says. Okay, things which are equal to same thing, that this is equal to this and this is equal to this, Okay, that means this is equal to this. They are same or equal. Okay, so we get AB is equal to AC is equal to BC. So all these sides are equal. So ABC is an equilateral triangle. Okay. Now there is an argument by some mathematicians. It says that Euclid assumed that two circles drawn with centers A and B will meet at C or meet each other. Okay. So Euclid only assumed that. Okay. Because it was not proved, only assumed that they will meet somewhere. The point is C. Okay. So this is what the argument says. Okay. And the third one, read this very carefully. This is very tricky. Okay. Two distinct lines cannot have more than one point in common. Okay. That is to prove that they have only one point in common. We have to prove this. Okay. Proof. Consider two lines L and M. L and N. Okay. Let us assume that these two lines intersect at two distinct points P and Q. Okay, we are assuming it. Let us assume that these two lines they intersect and they intersect at two points P and Q. Okay, now see the argument here, very intelligent argument. Okay, so there are two lines passing through P and Q. Got it? There are two lines, this line and this line. Okay, there are two lines passing through P and Q. We're assuming that there are two distinct points P and Q. Okay, now see this, try to understand this statement and try to understand this statement. Okay, and then go ahead. But we have an axiom that only one line passes through two distinct points. Okay, we are saying that, see, two lines passes through distinct point P and Q. Okay, but axiom says that only one line passes through two distinct points. If these are two distinct points, then only one line should pass. Okay. So above two statements contradict each other. Got it? Try to understand this. Okay. So our assumption given above that these two lines intersect at two distinct points P and Q is wrong. Okay. So we have what we have assumed was wrong. Okay. So P and Q coincides. So these are not two distinct points. This is only one point. Okay. Hence common two lines L and N. Got it? Therefore, two lines intersect at only one point, or the statement can be placed like this: two distinct lines cannot have more than one point in common. Okay. Try to understand this properly, because we will come across such type of proofs frequently in this topic. Okay, rather than not only in this topic but in geometry, whole geometry. Okay, solving some exercise. Fourth one, give a definition of each of the following terms. There are five given here: parallel lines, perpendicular lines, line segment, radius of a circle, and square. Okay, you have to give the definitions of all these. Okay, is asking the second part of this question: are there any other terms that need to be defined first? So for defining these, do we have to define anything first? Okay, then define this. That is what is he's asking. And if that is the case, then what are they and how might you define them? Okay, we will try to answer the whole question. We are taking one by one. See answer. We are taking only parallel lines first. Parallel lines. So definition of parallel lines is the lines, if produced indefinitely on both the sides, will never meet or intersect. That's the definition of parallel lines. Okay, or we can give another definition also. The perpendicular distance between the lines are equal at any point. Okay, now we will try to understand this. This is a line A, this is a line B. Okay, and if you find a line or a segment perpendicular to this and this, okay, and if making angle 90 on A and on B, okay, then you note down this distance, okay, and at any point if you find it like this, okay, at any point the distance will be, or this line segment will be equal. Okay, that means if these lines are produced, they will again never meet. That is the definition of parallel lines given here. But see the comment here, line A and B are parallel to each other, and these are written as A parallel to B. Okay, I was talking about this. In this, perpendicular distance is to be defined. This is to be defined. Okay, he's asking what are the other terms need to be defined. Yes, for this definition of parallel lines, you have to first define perpendicular distance. Okay, so what are they? We have given that, and how might you define them? Okay, this question will be answering. Okay, second one, perpendicular lines. We were trying to define what is perpendicular distance for the previous case. Okay, this is the same thing. We are now again trying to define what is perpendicular lines. Read this very carefully. The line intersecting at right angles are called perpendicular lines. Okay, now here a right angle is to be defined. Okay, so for defining something else, you have to define another thing. Okay, some other term. Now take these two lines E and F, and they are intersecting at a right angle. These are the two angles. Okay, and is written as E is perpendicular to F. Third one, line segment, a part of line which terminates at both the ends. This is a line, and this is a part of that line. Okay, P and Q. Okay, it's terminating here. That segment, you're talking about the line segment. Okay, so here part is to be defined. What is part of line? Okay, so line segment PQ is written as PQ and bar on this. Okay, fourth one, radius of a circle, a line joining the center of a circle to any point on the circle. That is radius of a circle. Okay, the circle, and this is a line joining the radius. Okay, now here what is to be defined? Okay, center is to be defined. So for defining radius, you have to define center first. Okay, and fifth one, square, a parallelogram with all sides equal and all four angles are right angles. Okay, look at this. This is a parallelogram. Here all sides are equal. Okay, and angles are 90. So this is a square. Here parallelogram and right angles are to be defined. Okay. Now the fifth one, very interesting. Okay, try to understand this properly. I am reading it. Consider two postulates given below. These are the postulates given by author. Okay, first one, A, given any two distinct points A and B, there exists third point C which is in between A and B. We just read it. Okay, and second postulate, there exist at least 3 points that are not on the same line. These are the two postulates. Okay, Now we have to answer some questions here. See, do these postulates contain any undefined term? It's talking about this and this. Okay, we will answer this. Are these postulates consistent? And third one, do they follow from Euclid's postulates? Okay, and I will to explain it. Now we will take answer for the first one. A, what is that? Given any two distinct points A and B, there exists third point C which is in between A and B. The first one, do these postulates contain any undefined term? This is a question we have to answer for this postulate. So this is the answer here. The term in between A and B is undefined term. Okay, this postulate does not explain what is in between A and B. Okay, are these postulates consistent? So yes, this postulate is consistent. Okay, and do they follow from Euclid's postulates? And I giving explanation for this. This postulate do not follow Euclid's postulates. Okay, so this is the answer for A. Now we will read B. There exist at least 3 points that are not on the same line. Okay, do this postulate, now we are talking about only this, contain any undefined term? So B, no, this postulate does not contain any undefined term. Okay, because this is very simple postulate. Okay, now second answer, are these postulate consistent? See, it is here. This is a consistent postulate. Okay, you know the meaning of consistent. Okay, and third one, do they follow from Euclid's postulates? Okay, no, Euclid has not postulated about 3 points not in the same line, but Euclid axiom says that there is a unique line passing through 2 points. Okay, so try to understand this. If you get confused, then write to me in the comment section and I will explain you again. Okay, and the sixth one, A, there are two parts in this. We will solve one by one. First one, A, if a point C lies between 2 points A and B such that AC equal to BC. Look at this figure. Point C, point C lies between 2 points A and B, between 2 points A and B, such that, explaining the position of C, AC equal to BC. That is AC, this segment is equal to BC, okay, or CD. Then prove that AC is equal to half AB. AC is equal to half of this. Okay, explain by a drawing figure. We will take this part afterwards. Okay, we'll just look at the figure A, C, and B, and this is according to the condition given here. So theorem: if a point C lies between 2 points A and B such that AC equal to BC, it's given here, we have converted into theorem, then prove that AC equal to half AB. Now this is again we have to write to prove that AC equal to half AB. Now proof. Okay, AB equal to AC plus CB. AB equal to AC plus CB, CB or BC. Okay, but AC equal to BC, AC is equal to BC, that's the condition given here. Okay, so we get for this BC or CB, we write another AC. So AB equal to AC plus AC, that is equal to 2AC. To bring these two down here, that is therefore AC equal to half AB. That is what we have to prove or here. Okay, so this is the proof for this. Exercise 6 again, part B. Read this very carefully. Is the extension of the previous part. Okay, if A point C lies between two points A and B such that AC equal to BC. This is same as the previous one, and there is something else also given. We'll read it. Then if point C is called the midpoint of the line segment AB, if this is a condition, then C is also called as a midpoint of the line segment AB. Okay, this is what is given. What you have to prove it is given ahead. Prove that every line segment has one and only one midpoint. Explain by drawing figure. Okay. Now answer for B. This is a figure AB. This is a C, and AC is equal to CB or BC given here. We are looking it as a theorem. The theorem, if point C lies between two points A and B such that AC equal to BC, so it's given. Okay, then we have to prove that if C is called the midpoint of the line segment AB, and under this condition C is the midpoint of the line AB. Okay, prove that every line segment has one and only one midpoint. Okay, whenever you come across some such statement or some such condition that you have to prove that there is only one, maybe now in this case the midpoint. Okay, we will come across some such situation, then you have to always consider that let us have more than one point, in this case midpoint. Okay, so proof, let us consider that AB has two midpoints C and D. Okay, like that we have to approach. Okay, so D is also a midpoint, we are considering that. Then if this is a midpoint, then AD is equal to DB. AD is equal to DB. Okay, first one. But as C is midpoint of AB, this was given. This is what we have considered. This is what is given. Okay, then we have AC equal to CB. AC equal to CB. Okay, subtract 1, subtract this from 2 from this. So AC minus AD, left hand side, AC minus AD is equal to CB minus DB. Okay, so AC minus AD is equal to CB minus DB. Now if you see AC minus AD is DC. This minus this is DC. Okay, so CB minus DB is minus DC. Got it? Very easy. AC minus AD is DC because AC was a larger. Then CB minus DB is minus DC. Very simple. Okay. If you take like this, then you get 2 DC equal to 0. That means DC equal to 0. Got it? This is possible if C coincides with D. Okay. DC is 0 only. So it shows that there is only one midpoint. Okay. So that is how you have to approach and try to prove. Okay. Always remember, we will come across many such examples in this part of geometry. Okay. This is Dr. Bharat Parab helping you in your studies. If you have any difficulty in this topic of use or applications of postulates in Euclid's geometry, let me know through comment section and I shall solve it. Thanking you. Good luck.